Okay, well, welcome everyone. It must be about time for a final exam if you're watching this video. What I'm going to go over here are a series of review problems for the final exam. So I don't have sort of a practice exam like I've had for the other tests, but I do have kind of a whole set of problems here that go over pretty much all the issues that we've encountered over this semester and things you should be ready for on the final exam. So let's jump right in. The first question here, write formulas for the following compounds. So this is going all the way back to chapter 2, polyatomic ions, charge of metals, that sort of thing. Aluminum hydride, that would be aluminum, which would be a +3 cation. And this would be the anion form of hydrogen, or H with a minus charge. So the correct formula there would be AlH3. We've got to balance out the charges between the cations and the anions because our neutral molecule or ionic compound should have no net charge, right? And you don't put any charge there when you write it out, just AlH3, and the charge is balanced. Iron 2 cyanide, the 2 there in parentheses, that tells us what the charge on the iron cation is. This would be iron +2. Cyanide is a polyatomic ion, Cn with a negative charge. So we again have to balance charge here. There should be 2 cyanides for every iron in our final formula. So we'll put a parentheses around the cyanide, right, and the 2 would go outside the parentheses, indicating 2 of the polyatomic ion. Chromium 3, similar issue there. That's telling us the charge on the metal, so that would be chromium 3+. Sulfate is SO4 with a 2- charge, right? And this 3,2 issue is something we've seen before. The least common multiple will be the first place we can balance the charges. That means we would need 2 chromiums and 3 of the sulfates in the final compound in order to have them balance out charge-wise to correctly give us the ratios for the ionic formula. Mercury 2 perchlorate, that's mercury with a +2 charge. Perchlorate is ClO4, and that has a -1 charge. So similar issue there, in fact, same ratio as we saw for iron and cyanide. This would be 1 mercury, and then ClO4 would have to be present twice to get the right compound. And then ammonium phosphate, those are both polyatomic ions, right? But those are both ones that we should be very familiar with at this point. Ammonium has a +1 charge, phosphate a -3 charge. So this time we need more of the cation, so we'll need 3 of the ammoniums and just 1 of the phosphate in that particular formula. So hopefully at this point you're pretty familiar and comfortable with your polyatomic ions and your ionic formulas. That will still, that'll always be something that is going to pop up pretty much everywhere as you're going through learning different aspects of chemistry. Okay, second question here. Balance the following equation. So just looking at it, there's 1 iron on this side or 2 irons on the reactant side, 1 on the product side. I would try a 2 there, see if that works out. Carbon in the carbon monoxide and carbon dioxide, there's 1 carbon in each, so those will have to be the same. Now, that might be worth considering. How will I balance the oxygen with the oxygens here? So if I have 3 carbon monoxides and 3 carbon dioxides, that would give me a total of 6 oxygens on this side and 6 over here, and that would also balance the carbons, so that would be balanced there. Now hopefully on a test I'll remember to put a space in there so you can write in your coefficients and maybe it's not quite so squished as you do it, but I think it's still understandable what we're doing there. Okay, once that's balanced, how many grams of carbon monoxide are needed to react with 3.02 grams of the Fe2O3 or iron 3 oxide? So that's a stoichiometry calculation. It's going to be based on units. If we start with 3 grams of Fe2O3, right, we want to work our way to grams of the other reactant. that will mean we need to convert from grams to moles. We'll find our handy periodic table, and we'll calculate some molar masses. So Fe2O3, 2 irons, and iron is 55.85 from my periodic table, and 3 oxygens, which is 16 for an oxygen. Right, so I'll multiply those by how many there are and add that together. So that would be 2 times 55 and 3 times 16. And my calculator warm up here, 55.85 times 2. And then 16 times 3 is 48. So let me just add 48 to that answer. That would be 159.7 grams in a mole. So 1 mole of iron 3 oxide would weigh 159.7 grams, and that would cancel out my units. And now I've got moles of iron 3 oxide. Now that means I can look at my equation, because my equation tells me for every 1 mole of the iron 3 oxide that reacts, 3 moles of carbon monoxide are going to react. This allows me to change my units to moles of something different, the carbon monoxide, right? And then I would just need one more step to get to grams of carbon monoxide, and that will be molar mass again of carbon monoxide in this case. So 1 mole of carbon monoxide, how much does that weigh? Carbon's 12.01, oxygen is 16. We can do that one without having to go and write them down separately. That would be 28.01 grams. Right? Moles CO cancels out, and this would give us the mass of carbon monoxide that we would need. So 3.02 divided by 159.7 times 3 times 28.01. That is, and 3 significant figures from the data we started with there, 1.59 grams of carbon monoxide. Okay. Pretty straightforward stoichiometry problem, right? You might want a little more challenge. That's going to come in the second example there. If reaction starts with 25 grams of the iron compound, 5 grams of CO, carbon monoxide, how much iron can be produced? So 2 different amounts here for the reactants. This is a limiting reactant problem, right? And that means we need to figure out which one is the limiting reactant in the process of figuring out how much product is produced. So what we want to do is calculate how much iron can be made, since that's the answer we're looking for. But we want to do that from each of the reactants. That way we'll be able to identify which one is going to run out first, which one is the limiting reactant. So starting from mass, I want to go to moles. Now we just calculated that molar mass, so that'll help with this problem. It's 159.7 grams of iron 3 oxide per mole. Since we're trying to make iron, right, back to the balanced equation, 1 mole of the iron 3 oxide will produce 2 moles of iron. So 2 moles of iron are going to be produced for every 1 mole of iron oxide that reacts. Now, how much? That's a little bit of a nebulous way to write the question, because moles could be a quantity of how much is produced. I think it's more likely this would be grams, so let's just add one more step. We'll calculate mass and we'll compare the masses. But a question that just asks how much, that could be grams or moles realistically in terms of your answer. So maybe you could just stop at moles, but let's go to grams. I think that's a little more likely how the problem would be worded. Okay, 25 divided by 159.7 times 2 times 55.85 would be 17.5 grams of iron. Right? Now that's, if we use up all that iron oxide, according to this reaction, we'd get that much iron. Maybe that's the answer, but maybe not. We have to try out the other reactant and see how much could be produced if we use up all of that reactant. So if we start with 5 grams of carbon monoxide, right, we had that molar mass above as well. 1 mole of carbon monoxide is 28.01 grams. From the balanced equation, 3 moles of carbon monoxide are reacting to produce 2 moles of iron. So that's a 2, a little bit like a 1, the way I first wrote it. And if we want grams for comparison, we'll do the molar mass of iron here again. 55.85 grams of iron is equivalent to 1 mole of iron. That would give us the mass of iron that could be produced if we use up all of the carbon monoxide. So 5 divided by 28.01 times 2 divided by 3 times 55.85. 6.65. That is a much smaller number. That means carbon monoxide is our limiting reactant. We're going to run out of carbon monoxide once we've made 6.65 grams of iron. That would be the answer to the problem. In this case, there'd be a lot of the iron oxide left over, right? That could be the next part of the question, right? How much of the excess reactant is left over? That would be kind of a nice question to put on a test. That is not the question on the practice problems here, though. And we're at a point where we should switch videos. So I'm going to stop the video there. We'll pick up on the next page in the next video.